Hello. Today we're going to build upon the work we did last week in edge detection in images. You will recall that the end result of the canny edge detector is a two-dimensional array of points corresponding to pixels in the image that represent edges. Essentially, it's a series of dots that join together to form edges, lines separating regions of the picture that are different colours. But that's all we have. What we specifically don't have is an artificial intelligence application that reports something like, this is an image of a car, or this is an image of a house. Today we start looking at the Hough Transform, which takes us one step closer to that goal. The Hough Transform detects basic shapes in edge-detected images. In its original and simplest form, it could spot the presence of straight lines, but it has been extended to detect circles and other simple shapes. Today we'll just concentrate on the straight lines. Beyond the Hough Transform, an AI program would detect objects based on the straight lines that Hough had found. Now I should point out that this lecture will be a bit heavier on the maths than normal. You don't need to be some sort of professor to follow it, but a nodding acquaintance with straight lines on a graph and trigonometry would be useful. Here's a straight line on a graph. It has a certain slope, or gradient, and an intercept on the y-axis, which is the height above the origin that the line slices through the y-axis. In this case, the line cuts that vertical axis at a height of 10, so the intercept is 10, and a bit of basic maths will tell you that the gradient is 0.5. Below the graph, I've given the standard equation representing this line. You will probably already know that any straight line, with the exception of one particular type, more on that later, can be represented by the general equation y equals mx plus c, where x and y are the coordinates of any point on the line, m is the gradient of the line, and c the intercept on the y-axis. In the case of this particular line, the equation is y equals 0.5x plus 10. Any straight line is defined by its gradient and its intercept, and we can represent those values on a different graph, one that plots m along the horizontal axis versus c up the vertical axis. The line y equals 0.5x plus 10 is represented on this new graph by the point 0.5, 10. What about a single point on a graph? How would that be represented when transferred to an m versus c graph? Take a look at the point x equals 3, y equals 5 on the graph. If we want to get an m value and a c value for that, we need to find a straight line that passes through that point. Well, the line y equals x plus 2 would fit the bill, and I have marked that in red on the xy graph on the left. That line has a gradient of 1 and an intercept of 2, giving us the point m equals 1 and c equals 2 on the graph on the right. The trouble is that y equals x plus 2 isn't the only line that passes through the point. So does the line y equals 2x minus 1, marked in green on the xy graph. From this we get another point on the m versus c graph, for m equals 2 and c equals minus 1. And here are two more lines that go through the same point. Y equals 0.5x plus 3.5, with a gradient of 0.5 and an intercept of 3.5, and y equals 5, which has a c value of 5 and a gradient of 0, so the x term disappears entirely from the equation. Each of the lines through the point 3, 5 gives a unique m value and c value, and hence a different point on the graph on the right. By now, you will have spotted that the corresponding points on the MC graph all fall in a straight line, with its own gradient and intercept. In fact, there are an infinite number of straight lines, each with its own m and c values that could go through the point, and their m and c values all lie somewhere on that straight line on the MC graph on the right. This is a general rule. Straight lines on the normal XY graph translate into single points on the MC graph. Single points on the normal XY graph translate into straight lines on the MC graph. So how does this apply to edge detection exactly? Well, suppose the points on the XY graph aren't just simple points. They are part of a detected edge, the sort of thing that the canny edge detector might produce. Of course, there might well be gaps in the line. As you saw in the last lecture, the canny edge detector is so strict about what it classes as an edge and what it doesn't, that we ended up with edges being split up into chunks, with sizable bits being missed altogether. But from the graph on the left, our edge detector has tracked down 4 points in the image that form a straight edge. How can we find the equation for that edge in the form y equals mx plus c? As we've just seen, each of those points could lie on any one of an infinite number of straight lines, and each point produces a straight line when displayed on the MC graph. I've shown 4 possible straight lines, each colour-coded, so that you can see which of the edge points it came from. Now, although there are an infinite number of straight lines that could go through each of the edge points, there is only one line that goes through all 4 of them, and that's the line whose equation we want. This corresponds to the single point that all the lines on the MC graph have in common, the one point where they all cross. Since that crossing point is on every single one of those coloured lines, it corresponds to a line that goes through each of the coloured points, the edge line itself. All we have to do is find the crossing points of all those lines, turn it into an M value and a C value, and bingo, we have the equation of the edge line. This is the simplest form of the Hough transform, where each of several edge points is turned into a line on the MC graph, and some sort of mathematical method, simultaneous equations probably, is applied to find the crossing point. Easy. Lecture over. We can all go home. Except, of course, we can't. There is a fly in the ointment that ruins the whole thing, and some of you will have already spotted it. The problem is vertical lines. A vertical line on an XY graph cannot be represented in the form y equals mx plus c, because the gradient is infinite. The equation of a vertical line is written as x equals a number, in this case x equals 2. If we could promise that the edge detector would never come across a vertical line, then we might be able to ignore this problem, but as you can see, we live in a world full of vertical lines. Fortunately, there is another way to represent the equation of a straight line, and that's using a distance p and an angle theta. P is the minimum distance from the origin, the 0 point where the axes cross, to the line, which is the length of the line that joins the origin to that straight line and hits it at 90 degrees. Theta is the angle measured anti-clockwise from the positive x-axis, what we might call the east direction on the graph, that this shortest line forms. The example on the screen shows the line y equals 0.5x plus 10 cast into the p theta form. The general form of the line is p equals x cos theta plus y sin theta. And for this particular line, a bit of mathematics shows that theta comes to 116.565 degrees and p is 8.944, both to 3 decimal places. It might be hard to accept that such a weird-looking equation could represent a straight line, but it is easy enough to show. Try picking simple values for x, such as 0, 1, 2, -1 or -2, and then put them in both equations. You will find that the values for y that you calculate as a result will be identical. Well, allowing for rounding error, of course. The advantage of the p theta form is that it can represent any vertical line. Take the line that we saw before, whose equation we normally give as x equals 2. In this case, the shortest distance from the origin to that line is 2 units, found by starting at the origin and moving 2 units to the east. This also gives an angle, theta, of 0, since that shortest distance segment lies flat on the x-axis. Putting these values into the general equation gives the equation that we started with, x equals 2. When it comes to the Hough transform, we can treat the equation of the line in this new format in much the same way as we did with the y equals mx plus c version. Any given straight line has a unique combination of p value and theta value, and corresponds to a single point on a graph of theta plotted against p, just as it would do if plotted on a graph of m against c. We generally plot theta along the horizontal axis and p up the vertical axis, as, from the equation, it's a great deal easier to get a value of p if you specify a value of theta, rather than calculating theta from p. Think about it. If you put in the value of theta into that equation, you only have to crank the handle once and the value for p drops out. If you put in the value of p, you have to mess around with sines and cosines and square roots and all that nonsense to calculate theta from it. Nah, stick to specifying theta and working out p from that. The surprising thing happens when we try to represent a single point on the ordinary graph on the p versus theta graph. In the case of the y equals mx plus c form, this came to a straight line on the MC graph. However, if we try the same thing here, it comes to a sinusoid curve. I suppose that really shouldn't come as too much of a surprise. After all, you can't work for too long with sines and cosines before you start seeing curves like that. Remember this? This is where we had several points on our XY graph that clearly represented points on a straight line, or a straight line from an image. The sort of thing that our edge detector might produce. Each of those points in a dead straight line produced its own straight line on the MC graph, and the point where they all crossed gave the gradient and intercept for the edge itself. Well, if you do something similar for edge points, using our new representation of a straight line, you get this. Now, each of the points produces its own sinusoid curve, and they are continually crisscrossing over each other. However, there is only one place where they all meet, and, just as before, that gives the equation of the straight edge on the image. Of course, the equation comes out in the form of a p-value and a theta value, but a bit of straightforward maths can convert it to a gradient and intercept if you want. Needless to say, but I say it anyway, getting that p-value and theta value is the devil's own job. It can be done using simultaneous equations, but do you fancy solving large numbers of simultaneous equations, each of which contains sines and cosines? No, me neither. And the problem becomes a great deal harder when you consider the fact that there may well be more than one straight edge in the image. If there are two straight edges, then that gives two sets of sinusoid curves, all overlapping each other, in a massive tangle on the p-theta graph. The whole thing starts to look like that pit of snakes from the first Indiana Jones movie. Now you have the added task of determining which sinusoid curves go with which set of points. We can get round both those problems with a dodge. Instead of solving the equations mathematically, we allow each equation to vote for a different edge line. Here's how the procedure works. We set up the horizontal theta axis to go from minus 90 degrees to plus 90 degrees. All edge lines can be represented in p-theta form by a line with a theta value in the range minus 90 to plus 90, provided we also allow p to be negative. Then repeat the following procedure for each isolated edge point that we found on the XY graph. Go through all the possible theta values from minus 90 to plus 90 in small steps, maybe in 1 degree steps, maybe even smaller steps, such as 0.1 degrees. For each value of theta, calculate the corresponding p-value given the XY point we're considering. That point on the p-theta graph gains 1 vote, as it is present on the sinusoid curve for that XY point. Once we have been through all the theta values for that edge point, we end up with a sinusoid wave of votes, as you might expect. And you get something like this. Most tutorials on the Hough Transform contain an image similar to this, which shows the votes cast as white lines on a dark background. Looks like something you'd want to run a hairbrush through, doesn't it? The points where many of the lines come together appear as bright spots. These points have accumulated the most votes and are duly elected as the p and theta values for edges in the original image. Each bright white spot represents a straight edge in that image. Clearly whatever was in this picture had 10 straight edges. Of course, these curves are continually crossing each other without producing white spots. If we took every single crossing point as an edge, then there would be hundreds of them, the equivalent of assuming that every pair of edge points that the edge detector produces actually represents a genuine edge. In practice, the program would set a threshold for edge detecting. If any point on this diagram, and it seems more appropriate to call it a diagram rather than a graph now, gets fewer than a certain number of votes, 10 maybe, then it's not a proper edge, merely a small list of points that happen to lie in a straight line. You will also notice that some of these white spots are rather blurry, such as the 3 lower ringed points in the centre of the screen. Others are quite tight, such as the ringed point just below the top one in the screen centre. The tight crossing points indicate that the edge points that gave rise to it are in an equally tight straight line. The blurry ones happen when edge points are roughly in a straight line. How strict you are about this depends on you. You might insist that edge points only count if you could join their dots with a ruler, in which case you would insist on votes only being counted based on small areas of that diagram. increase the resolution of theta and p values, perhaps determining the theta values to 0.1 degree rather than 1 degree, and the p values to 2 decimal places rather than 1. On the other hand, if your image is rather grainy or low quality, then the proper edge points that produce it might not be in a perfect straight line, so you'd want to allow votes to be cast for larger constituencies, determining the values of theta to a resolution of 1 degree. Votes counted on that diagram will be for small areas rather than exact pinpoints. It's horses for courses, really. By this stage, we have learned the basics of the Hough Transform. Here you can see a list of the steps involved. Firstly, it only works on edge-detected images, like the ones we were talking about last week. Don't try it on unprocessed images. Secondly, create a two-dimensional grid of numbers to hold the votes. The x direction will be the theta angle, and that spans from -90 to +90 degrees. The vertical axis will represent the calculated p values, and they might be either positive or negative. Set all the votes to 0 initially. Now take each edge point in the processed image and work your way through the theta values from -90 to +90, calculating corresponding p values. For each combination of p and theta, increase the vote for that cell in the voting grid by 1. After all the edge points in the image have been treated this way, a large number of cells in the grid will contain at least one vote, and some of them will contain relatively large numbers of votes. Any cell that contains a number of votes above some arbitrary threshold corresponds to a straight edge in the image. Read off the p and theta values for those points, and they will give you the equations for those edges. That's it. That's the Hough Transform. The question is, what to do with those equations? Well, we've got the equations of our edges, but that's only half the story. After all, an equation gives us a straight line that extends endlessly in both directions, whereas edges of real objects have fixed starting and stopping points. Take a look at the edge points in this image. Clearly the original image contained a rectangle and a triangle, and the Hough Transform has detected the 7 edges present in the image, but it doesn't tell us where those edge lines should stop. It's tempting to assume that where these edge lines cross must be the corners of the shapes in the image, and therefore the ends of the edge lines. If you could be certain that there was only one shape in the image, just the rectangle or just the triangle, then that approach would work. A few simultaneous equations later, you would know the coordinates of those end points. However, with more than one shape, the algorithm could have no way of determining which edge lines should curtail which other ones. The most obvious next step will be to determine which point was on which edge. Then when an equation went past the final point on an edge in either direction, the computer would know to prune off the remainder of the line given by that equation. As well as stating that the equation of any particular edge was such and such, it would state that the edge ran from one particular pair of coordinates to another pair. From that data, it could then start to calculate corners of shapes from endpoints that were common to more than one edge, and so on up to actual object recognition. Points that make up an edge must, by definition, lie on it, or at least very close to it. Assigning a point to an edge would involve determining the shortest distance from each edge point to a detected edge, done with some fairly basic maths, with the edge the shortest distance away claiming the point as part of it. Again, there would have to be some sort of threshold to remove outlying spots that weren't really part of anything. This simplistic strategy is often used, but it does have its problems. Firstly, take a look at the lowest corner of that triangle. There isn't really a detected edge point anywhere near that corner, so the algorithm wouldn't know that the two edges that make it up ended at the correct place. It would prune off too much from the ends of those lines, giving two spurious endpoints that didn't lie in the same place. Secondly, some of the edge points that make up the triangle are perilously close to the edge lines for the rectangle, and vice versa. Based solely on the distances of the points from each calculated edge line, it will be so easy to assign the points to the wrong shape, and conclude that the edges extended far further than they actually did. A more sophisticated strategy is needed, perhaps one that looks for large sections of edge equations that didn't have any points on them. As they say, that is a story for another day. This part of object recognition is nothing to do with the Hough Transform. All that does is take a few edge points scattered over a processed image and turn them into a series of equations describing edges. If all this math has left you a bit shell-shocked, then a practical example will, I hope, help to clear things up. Next week, I shall be producing a JavaScript program that goes through the whole procedure and talking you through the code. Until then, thank you and goodbye.